looking for ways to involve students more in the mathematics and making mathematics more meaningful for them. I don't know what your experience was when you went through the K-12 system, but mine was very traditional. Kind of a Sputnik-era math program where the teachers told me what I needed to learn. I memorized it very well. I passed the test and promptly forgot it all. Finding a different way of thinking about mathematics didn't happen until actually I went back into the classroom as a teacher and discovered that I thought I knew a lot more about math than I really did. So the journey since I've left UConn and been a classroom teacher has been tremendous for me, and I want to share some of the things that I picked up as I've gone along. This presentation is an adaptation of one that I presented to the Mathematics Association of America's chapter here in Michigan a few weeks ago. So there are some things in here that I think you'll enjoy, and some things in here that are a little challenging for all of us. So we'll go along that route. I think I mentioned that mathematics is often taught in a way that kids kind of wonder why they're learning it. And I know as a teacher I was often told or often asked, why do I need to know this? And my first few years, I had to really struggle with coming up with answers other than, you need it for the test or you need it for next year's class. We need to find a way, and Whitcomb's article here, which the link is actually active if it works for you, and you have the resources to do that. It's a very short article that really kind of captured my interest in mathematics as a creative object rather than just a tool to answer a few problems. Mary Lindquist was the president of NCTM, and there's a preface in the book, Making Sense, Teaching and Learning Mathematics for Understanding from NCTM. And these two quotes really caught me. I can say that I've had students like this, that they'll follow the rules but not make any sense out of them, or they'll do things that aren't intuitively logical to them, but it seems to work and get the answer the teacher's expecting, so they go on that. And they're happy to do that because they get the grades that their parents like, and it moves them through the system. We also know that as we focus on sequential rules and algorithms, that kids' creativity tends to drop. There's some really interesting videos on my website there from Ken Robinson that talks about the death of creativity as we move our kids to the education system that you might enjoy. So I mentioned the way that I learn mathematics, and I like to call that the 3 R's: recite, replicate, and regurgitate. And I often told my 7th graders, what happens when you regurgitate? You don't retain anything, at least you don't want to at that point. And here's an example of this. It's a 6th grade problem where the children were asked to draw a rectangle with 3-centimeter base and a 4-centimeter height, and then shade 3/6 of it. The solution that a student came up with, I think, is very creative. But unfortunately, the teacher at that time was unsatisfied, or in fact marked it incorrect. And the way that he explained it to the researcher that he was working with is that he was forced to admit to the student, after the student challenged the grade, that it was correct. But then the next comment is what really kind of struck me. It's what you get when you don't tell the pupils exactly what to do. And then he tried to, how was he going to teach it so the kids wouldn't do these types of things? I would have hoped that these are the kinds of things I want to encourage, and I'm going to give you a couple of reasons why encouraging a creative approach to solving problems is something that we need to develop in our students. One very striking example was when I attended a conference at the Indiana University in 2007. I'm a retired Air Force officer, and I worked with some very, very competent Air Force Academy cadets during my career. And I can resonate with what the commandant said when he spoke at this conference. The cadets come in, they're extremely smart. It's a very competitive school, but they come out not as good problem solvers, but actually less creative problem solvers. And we spent a lot of time. In fact, there's a standard joke in my office. If you came out of the academy, it took 4 years of our time to untrain you to get you to be able to think more creatively and be more fluid in your problem-solving things. So we need people to understand why the rules are there and how the algorithms work, but we also need them to be able to create their own flow of things and to look at things in front of those types of activities. And people say, well, this is a new approach. This is something, Common Core-ish or new math-ish or whatever reform system you want to pick. But I contend that we've known this not just since 1894, but long before that as well. But I wanted to go back to the Committee of 10 report, which was hosted at Harvard University and sponsored by the National Education Association, that talked about the teaching and learning of mathematics. And the first thing I wanted to point out is that textbooks should be subordinate to the living teacher. Now, my job here at Hope is to work with pre-service elementary school teachers. And many of them come in telling me they chose to teach elementary because they didn't want to have to get into the tough math. Or even worse, that they didn't like math, so they chose to teach elementary grades. And yet, those are the grades that I believe are critical to developing an appreciation for mathematics. My students come in thinking that the textbook's going to be their salvation as they work their way through their teaching system, and I'm trying to get them to understand that the textbook is a resource and not the ultimate authority. What we want the students to be able to do is to draw the problems from things that are comfortable about this. And we talk about real-world connections in a lot of different curriculum courses. And we want the scholar or the student to be able to devise as many problems as he can. Most of us don't enjoy solving somebody else's problems, but really get invested in solving our own. And I think that should also be the case for students of mathematics. And then finally, out of this report, and it's an interesting report that you can find online. If you'd like a copy of it, I can be happy to send you a link to that. But what I really liked is that the rules should be derived inductively instead of being stated up front. My first year at Purdue, I was offered the opportunity to teach future high school math teachers, and I went in with what I thought was an easy question, which is the age-old, why do you invert and multiply when you divide fractions? And the answer I got uniformly from every one of them on their little survey was because that's the rule my teacher taught me. And so the next question was, why does that rule work? And it took 2 weeks before I had a student come back in and explain it to me. So either they weren't interested in understanding the rule, or it was so ingrained in them that they couldn't think past the rule to come up with the reason why it works. Some of the critiques now of the Common Core system is that we're not just teaching the algorithms, which are what parents are very comfortable with often when they're trying to help their students. But we're asking students to explore the way addition works or the way multiplication works and work them into the algorithm later rather than introducing it first. I'm a big fan of algorithms. I mean, I don't want to have to reinvent the wheel every time, but I want to understand how the wheel works before I trust it. So I think that's the same type of philosophy here in 1894. 2012, same type of thing coming out in the Common Core standards. We have the 8 standards of mathematical practice, which I really appreciate. One of the comments that I often hear from the faculty on the hallway here in the math department is that we have impatient problem solvers, students who give up very quickly on solving tough problems, and yet the tough problems are the ones we really want them to tackle. As you read down this list of 8 practices, you'll see a lot of things here that are very near and dear to the gifted education community as well. Being able to reason abstractly and quantitatively, being able to explain either by argumentation or critique and reasoning of others, using things strategically, which requires you to think a little bit about why you're doing what you're doing, some metacognitive approaches. One of the questions that I ask my pre-service teachers is that when you make a homework set, please be able to justify every problem that you've assigned. If you can't tell me why it's important for a child to spend 5 minutes of his life working on this problem, it's probably not appropriate for you to assign it. And one of the things I often see is now there's 5, 10, 15 problems all using the same tool over and over again. And we know that once you start doing that, the selection of the tool becomes automatic. The students don't have to make a strategic choice to think about why they're doing it. And that's very difficult then for them to understand how that tool works in different situations. A colleague of mine also at Connecticut often talks about rather than assigning 10 homework problems, assign a fewer, maybe even one homework problem, and have them solve it 10 different ways, and then evaluate the different strategies that they use to see which one's most effective for them. Precision is important. I want you to get the right answer, but I also want you to understand why the answer is right. The last one there, the ninth one, that Linda Sheffield, who's a friend who I've worked with in the past, and Sandra Johnson, I believe, who's at Baylor, being able to solve problems in novel ways and to propose new mathematical questions of interest to investigate. I'm going to share with you later in the presentation the story of Emma, and that's a very good illustration of that kind of an activity that I think kids would really engage in. Key focus here is we're going to, in Common Core, is fewer topics and focus on conceptual understanding. I'm not going to spend a lot of time here. This is more for my mathematicians when I talk to them, and I didn't see a whole lot in the audience poll at the beginning. But there's a really nice document at the University of Arizona's Institute for Mathematics and Education, and it's free. It's a progression document for the Common Core standards and talks about the rationale about how we develop different levels of understanding as the kids progress through those types of things. And so if you're doing classroom teaching, or if you're interested in more in the how behind the Common Core, I suggest you check this document out at some point. One of the focuses, though, on the standardized test is going away from the multiple choice activities. For example, the one on the left is from the California traditional standards test, where the child simply has to be able to apply the definition and select the correct choice out of the multiple choice test, as opposed to the one on the right, which is from a Smarter Balance test, where there is a description of a transformation on a triangle, and then ask the kids to explain the confusion, their conclusion. Very similar to the evidence-based questioning strategies that kids are now being asked to develop in reading tests. They're actually looking at justification and being able to support their answers on mathematics tests as well. And I think we'll see more of that, and I think that's a good thing. If you look at the 21st Century Skills Map in math, a joint activity by the three associations there at the top of the chart, we want kids to be creative and innovative, to look at new ideas and be able to demonstrate originality and inventiveness, to understand how the different parts of their problem-solving strategies fit together, and to make judgments on and select and strategically choose different types of techniques and tools to do that, and then to be able to explain and articulate their thoughts. I know many, many times I'd have students come in when I was teaching middle school and say, I couldn't solve the problem last night. And my first question is, what did you try? And they couldn't remember, or probably didn't make an attempt because they didn't understand what the problem asked. Often then I would ask my students, in fact, a standard request was, go back, try the problem again, write down 3 questions you want me to help you with to understand that. And that gives us a place to start the conversation, as opposed to what I hear often in even my college courses here, just show me how to solve the problem. That's not my role in life, because I'm not going to be there when those real problems hit. So I want you to be able to think about and collaborate with others about those problems. Carol Dweck does a lot with mindset and the power of believing that you can improve. That link there at the top is actually one of her latest TED Talks. And what we do know is that there's a perception that there are people that are good at math and people that are not good at math, and there is some basis to that on the way the brain develops, but we also know that it's not a fixed entity, that no matter where you fall in that line of academic or intellectual development or capabilities, we can make you better. But you have to be willing to understand and accept a growth mindset to look at that. And so another one of my favorite videos, again, is Carol's his TED Talk here. One of the things I was really struck by was the grading practice she discusses. I believe it's a Chicago school system that's doing that, where assignments are turned in and they're either graded as ready or not ready. And so students continue to work on assignments, very much a mastery type of grading system, until they are ready to move on to the next one. Much different than the types of grading systems where it's one shot and you're told whether or not you're an A, B, C, or D student which develops kind of that internal sense of where I belong and what I am. We also know from Project Challenge, which was done by Susan Chapin and O'Connor at Boston University, that conversation is very important in the classroom. And yet often I remember my first year of teaching, my principal was concerned that my math classroom was probably noisier than any of the other activities. But because my students were talking about math, they were discussing math, they were working on problems. This Project Challenge, and Susan Chapin has continued this work at Boston, and is one of the co-authors on the Project M Cubed and Project M Squared that Kendall Hunt publishes. They got the kids involved in talking and explaining their reasoning and building on each other's thinking. And what was really interesting is that third sub-bullet under there, where after 2 years, the proportion of students showing high probability of giftedness mathematics rose from 4% to 41%. And Project Challenge was done at a very low-performing school in Massachusetts. And to bring that up that significantly in just a 2-year time period is a tremendous achievement. So conversation is out there. It's an important part. There's a lot of research about discourse and ways to do that. Susan has some books out that I would encourage you to explore about questioning and conversational strategies. So those are other options to look at. When I was at Connecticut working on a dissertation topic, I came across Don Balka's work. He taught at St. Mary's College in South Bend, outside of Notre Dame, for many, many years. And I really like all of these ways that he identified creative ability, and in another talk I could illustrate how all these fit in. One is that we ask kids to formulate hypotheses. Think about what's going to happen and what the solution to the problem is going to be. And that's going beyond just estimating the answer, but actually thinking about relationships. We ask kids to look for patterns, to determine the structure and things, to be able to see how things fit together, and to get beyond those established mindsets of, I've got to go find the right rule, or I've got to look up the right equation to get to that, and to look at things, when those aren't available. How do you attain a solution to a problem? I remember Joe Renzulli took me down to New York City to talk to a bunch of high school teachers, and I posed a problem that intentionally had some information missing. One of the teachers in the audience was a football coach, and what I had left out was the width of the football field. He solved the problem very quickly. The other teachers were frustrated, but rather than asking a question, which kind of goes along with this fear on the be quiet in the classrooms, don't have a conversation with the teacher or with my friends, they worked very quietly trying to come up with an answer but couldn't find it. What they need to understand is that there's rules for variables. There's rules for developing mathematical models that would allow you to do that. And asking those questions is important. And then the other two here are also looking at unusual ideas, to think through consequences from different situations. For example, we were all taught parallel lines never meet, but I can show you examples even on the globe where they do. But until somebody asked those what-if questions, we didn't have this non-Euclidean geometry to build on, make those decisions. And yet non-Euclidean geometry explains our universe so much better than the world that we typically teach in a Euclidean kind of setting. And then be able to break problems into smaller groups. One of the things that I found in my dissertation, and this is the little chart here is actually from that, is that it's not necessarily the best student who scores the highest on an achievement test that is my most creative. Those 4 little arrows across the top are representative of comparable creativity scores on the tests that I use, between 44 and 47, and yet significantly different achievement scores on the Connecticut Mastery Test for mathematics at the time. There is a fundamental base of knowledge that you need to be creative in any discipline, and John Feldhusen's work kind of supports that. But after that point, creativity kicks in, and you can play with the knowledge in different ways. So I try very hard to look for creativity in all my students, not just my highest performing ones, to go from that along those lines. Let me go back one slide. I'm sorry. I went through that a little bit too fast. And I guess it's not coming back up. Dan Meyer, if you haven't seen his whole video, Math Class Needs a Makeover, I would again suggest that, and his link is actually there over in the link section. 5 symptoms that he talks about when we're developing math reasoning that tells us that we're doing it wrong is our students lack initiative. They don't pose problems in classrooms. They wait passively for us to give them something to do. When I really knew I was teaching well is when my kids came in the classroom and started throwing questions at me before I even got a chance to start the class off. And those were the days where we threw the textbook and the lesson plan out, and we spent the time focusing on their questions. And when I saw those were the best teaching days, those were the days when the bell rang and they didn't want to leave. Those were the days that made a difference on their test. Again, I mentioned impatient problem solving. Kids, we talk about the 30-second mathematician. If I don't see a way to solve the problem in 30 seconds, it must not be solvable. And yet the 30-second problems, those quick solutions really are exercises to develop automaticity and skills, but not really develop problem solving. We all complain about they can't remember things from year to year, and that's probably because we're not teaching it the way they remember it. We're afraid of word problems, and we're always eager to find a formula. I have a video clip from this that I'd like to share with you, and Robin, if you could key that up now, that would be great.
So I can diagnose the problem a little more specifically in math. Here's a really cool problem. I like this. It's about defining steepness and slope using a ski lift. But what you have here is actually 4 separate layers. And I'm curious which of you can see the 4 separate layers, and particularly how when they're compressed together and presented to the student all at once, how that creates this impatient problem solving. I'll define them here. You have the visual, okay? You also have the mathematical structure, talking about grids, measurements, labels, points, axes, that sort of thing. You have sub-steps, which all lead to what we really want to talk about, which section is the steepest. So I hope you can see, I really hope you can see how what we're doing here is taking a compelling question, a compelling answer, but we're paving a smooth, straight path from one to the other and congratulating our students for how well they can step over the small cracks in the way. That's all we're doing here. So I want to put to you that if we can separate these in a different way and build them up with students, we can have everything we're looking for in terms of patient problem solving. So right here, I start with the visual, and I immediately ask the question, which section is the steepest? And this starts conversation because the visual is created in such a way where you can defend 2 answers. So we get people arguing against each other, friend versus friend, in pairs, journaling, whatever. And then eventually we realize it's getting annoying to talk about the skier in the lower left-hand side of the screen or the skier just above the midline. And we realize how great would it be if we just had some A, B, C, and D labels to talk about them more easily. And then as we start to define like what does steepness mean, we realize it'd be nice to have some measurements to really narrow it down specifically what that means. And then and only then we throw down that mathematical structure. The math serves the conversation doesn't serve the math. And at that point, I'll put it to you that 9 out of 10 classes are good to go on the whole slope steepness thing. But if you need to, your students can then develop those sub-steps together. Do you guys see how this right here compared to that, which one creates that patient problem solving, that math reasoning? It's been obvious in my practice to me. And I'll yield the floor here for a second to Einstein, who I believe has paid his dues. He talked about the formulation of a problem being so incredibly important. And yet, in my practice, in the US here, we just give problems to students. We don't involve them in the formulation of the problem.
And I think I'm getting my slides back. As you were watching the video, I was looking at some of the comments in the chat box, and I noticed, I think it was Cindy who mentioned about most teachers, when I go in, tell me they can't do this because they have to cover the curriculum to cover the standards, and I understand that. I've been there. But I also understand that covering the standards, if you're not doing it well, probably isn't going to improve test scores all that much, or it's going to be an approach that doesn't stick. And one of the encouraging things about Common Core is that we're cutting down on the breadth and spending more time on the depth and the mathematical dispositions. However, I haven't found many curriculums that have made that change yet, and a lot of the professional development work and a lot of the practices that our teachers are comfortable with haven't yet fully embraced that. I don't know what it's going to take, because as I showed in the Committee of 10 stuff from 1894, and I have other books from around the turn of the century, from 1900 to 2000, from 1899 to 2000 to 1902-03. There was much written about changing mathematical teaching to look more at concept based. There's an interesting article in Harvard Education Review about how math education has developed over the years on a commerce-based activity. And as technology has become more and more helpful in eliminating the computational tasks, we need kids now to be able to think about the conceptual foundations of mathematics. So Dan's recommendation was to bring multimedia, to bring the real world into the classroom. And he has many, many samples of that online. One of his actually made it on Good Morning America, where he talked about a queuing problem based on which grocery line to get on based on the number of grocery carts and how much was in each cart, type of an activity. We want kids to be intuitive, so let them make some guesses on that. And I have some sample problems that I'll get to here in just a minute that I hope will do that. Ask the shortest question that you can. We tend to ask leading questions that kids have learned that, we have something specific in mind. And by asking a very short question, let them come back and ask for more information as they need that, which allows them to build the problem. And my biggest flaw my first year of teaching was to be too helpful. Sometimes I need to step back and then let the students embrace the struggle and develop that persistence that I so value in the employees that I had when I was working in a different profession. Just a couple of comments from some fairly well-known mathematicians. George Polya, we've all seen his work. If you walked in and looked at any problem-solving strategies in any textbook that's out there, Polya is going to be referenced. When we're all done, we have these very nice formal proofs, but it always starts with a guess. And a lot of kids are very uncomfortable with, what do you mean I can guess? Isn't there a rule someplace to do that? And it's not just George that talks about that, but Paul Halmos also talks about that. When we start, we make vague guesses. We visualize broad generalizations. We jumped on warranted conclusions, which sounds like a lot of the gifted kids that I've worked with in the past. But we're we have the conviction that our idea is right, and we're going to work very, very hard to make sure that we can justify that and prove it to other people. And so we embrace failure. We embrace taking risks. So we get discouraged, and we try over again. It's not that 30-second problem solver that we're trying to develop. One thing that's kind of really exciting, and because I teach at a liberal arts school, I'm kind of interested in this. There's an NSF program out there called Discovering the Arts of Mathematics, and right now those textbooks are available free online. Now, these are college-level courses, but they're designed for the non-math major. And I would think they'd be very appropriate, especially in high school courses for the gifted, and possibly even some middle school courses, depending on where your student is in their development of activities to do that. Some of the student comments that go along with the research that's been done on this is they were able to solve problems and make conjectures. The course was a breath of fresh air and helps them understand the connection between why math professors like math so much and what's going on in the classroom. I really like that comment about how beautiful it can be. I enjoy good music, whether it's classical or jazz or contemporary. I enjoy great art, but I'm not a performer. I can appreciate the product of their work and see the beauty and the creativity in it. I don't necessarily have to be the person that creates. And I think from a liberal arts perspective, even if you're not going on to be a mathematician, you need to understand that kind of thing. Just like I appreciate Hemingway's work as a reader, a consumer of that product, I'm not necessarily ever going to be a Hemingway. I like the fact that they talk about thinking independently, that embracing struggle and to embracing a struggle and want to find the answer because the problem isn't easy. There's a couple of really nice student interviews on YouTube, and if you have an opportunity after our conversation today, take a look at them. I think you'd be really impressed at the way the kids' thinking changed just over one course in a mathematics setting. And now I'd like to talk about a couple of mathematical concepts and then throw a couple of problems at you to think about. And that probably will wrap up our time together today. One of the comments in 7th grade that I often get from my students is that negative numbers don't make any sense. And I wanted to share with them the history of negative numbers. For a long time, it was only used as a computational tool. In fact, the ancient Greeks dismissed them altogether because they only worked in something they could create, and it's very hard to draw a line that represents a quantity -3. While they were used computationally by some people as a record-keeping activity, the controversy about whether or not they were real numbers or not existed for a long time, and there's a few different quotations from different mathematicians over time there on the slide. What I really like is the last one where it says, such mental aberrations could prevent gifted minds from studying mathematics. What I think is really important is that my 7th graders now understand that not only are they struggling with mathematics, with the concept of negative numbers, but some of the greatest mathematicians over centuries had this debate about whether or not we should even look at those. The next slide asks the question, why is the product of two negative numbers positive? And if you've ever taught negative multiplication of negative numbers, you've probably heard this question. Here's one way to explain it, a fundamental question dealing with the property of operations of numbers. It's obvious the product has to be A times B, but what the sign is not so obvious. It can't be negative A because negative A times positive B or negative B times positive A would give us negative AB. So it can't have the same result. So, by definition, it must be positive. And I throw this out to mathematicians, or I throw this out to students, and they say, that's not very satisfactory. But the person who came up with this was Euler in 1770, someone who's a very respected mathematician. That's the best he could come up with at that point in time. Often it's taught by the rule of signs, so we all go off and memorize the rule or some mnemonic. I remember my 8th grade students had come from 7th grade where they were taught a little jingle to remember on how to do this, and when we got to a pretest on negative numbers, I heard them humming it under their breath, and some of them were actually doing hand movements to kind of remember that. So rules and rhymes, direct instruction, different models help us develop that. But there are some other ways that we could develop that understanding. Does it make sense that the product of two negative numbers is a positive quantity? We could look at patterns. And as we multiply numbers together, there's a pattern that develops. And not real satisfying, but it kind of makes sense that if negative 2 times 3 is negative 6 and negative 2 times 2 is negative 4, as we move through that progression, the pattern follows something that seems logical. We could look at it inductively. So what if the product of two negative numbers is positive? And in this case, let's just use something simple like negative 1 times negative 1. Then we can do some little algebraic functions. And again, if this algebra isn't in their skill set yet, I would not want to do this with students. But if I take negative 1 and I add 1 to each side, I can actually show that 0 equals negative 2. If you spend a minute looking through this, I think you can follow this rationale. I take -1 times the sum of 1 times -1. 1 plus -1, that works out that way. Or I can go one more step and I can look at it algebraically, and in this case, it works out that -1 times -1 is a positive 1. So there are different ways I can show students to look at this and help them make sense of it. But really showing them any one of these three is not sufficient. Once I've shown them these, I want them to come back now and explain it to me in their own words. Which one seems most reasonable and why, so that they don't have to remember that little jingle that some other teacher taught them, but they can explain to me the pattern behind multiplying negative numbers. And I promised the story of Emma, and just to let you give a little background. Emma is a student, or was a student, at a private school in the UK. A very diverse classroom. Most children were between 9 and 11 years old, and I've heard Emma on both ends of that spectrum, so she was somewhere between those two age groups. 3 different ability levels, and most of the students were non-English language students or non-UK background, so a very diverse classroom. The teacher posed this problem, and there's some prep work that was done before this, but in a differentiated classroom, he posed this problem to come up with a hypothesis, and I really like his use of the word hypothesis because it phrases the problem in a different kind of sense. Is there a connection between the number of sides of a polygon and the number of diagonals you can make? From this perspective now, the kids are asked, there are no numbers in the problem, so they're asked to think about, what is the relationship here? It's much more a research question, very loosely structured, not a lot of information, and there's a cause and effect relationship here. So kids are starting to see how things fit together. Here's Emma's work, and there's a couple of different versions of this depending on which of the articles Casey wrote. And when I've shared this with other teachers, and there's 3 slides here that show her work, they've said if I could get my students to work like that, I would be really excited. So I'm hoping that as you're looking at this, you start to see some things that kids could do. First, she restates the challenge in her own words, not much different from the way her teacher did that. She drew some pictures. She did some sketches, and in our work at Connecticut on mentoring mathematical minds, we purposely put doodling space or space for mathematical doodles on any worksheets or any activities we gave kids because we want them to draw pictures. You can't walk into a mathematician's class office anywhere I've ever been and not find scraps of paper with drawings on them or sketches on blackboards or whiteboards while they're trying to make sense of things. Then she notices that the number of sides -3 is the number of diagonals. Using the right vocabulary, documenting what she notices, and for some students, now I'm done. I've seen a relationship, but that's not enough. And going back to Polier's work, once we've made a guess, we need to start developing that, proving it, justifying it, making sure that we understand those types of things. And now we start to see some of the problem-solving strategies that you might be teaching, making a table, stating a rule, drawing sketches, looking at simpler problems. And if you'll notice, Emma started with a very simple diagram and added more and more sides. So she started with a simple problem and worked with the more complex. She makes it tables. Now she comes up with what she thinks the rule is. It's the number of sides -3 times the number of sides divided by 2. She tests the rule a few times, and then she comes back and she makes a prediction. So she's now taking it from the specific to the general and comes up with a couple of activities here and then tests that. A couple of things here. There's a notation error. The way she has written her formula will not generate the data chart. The order of operations doesn't work here. Her parentheses are in the wrong case. Some teachers would mark that wrong. To me, that's not a wrong answer. That's a teachable moment. I can ask her we can talk about order of operations and why we do it that way. And for those of you who are history buffs, the convention for order of operations was still being debated in the 1920s. So conventions change, and the way things are written are different at times. And then at the end, she comes up with strangely, in my pattern, double the number is not double the diagonal. So here's an opportunity now to take a question that or something that she's noticed in her solution, generate a new question, and build on. As I talk with mathematicians around the country, that's where their research ideas come. They solve one problem, but that one problem spawns several more. And there's the beginnings of a new problem here for Emma to go off and study. This is a lot of words, and I want to point out just a couple of things. And afterwards, you can read Emma's voice and her conversation with her strategy behind that. First of all, she searched for finding a connection. She wasn't looking for formulas, which is where a lot of my students start. Just tell me how to solve it. But what's the connection between the number of sides and the number of diagonals? Then she came up with a strategy. And she didn't use just one. She used several throughout that. And then she talks about noticing and wondering. And those are terms that I often don't hear in classrooms, especially the wondering one. What's going on? You know, I'm really trying to get my students away from just punching numbers into a calculator, and now it's getting to the point where you just pick up your phone and you ask it to solve an equation for you, and it can do that. I want that sense of wonder, because if you don't have that, you don't know what questions to ask. What's even more important is the change in Emma's teacher's way of looking at things. The first point that he makes is that he's startled at what children can achieve when they're trained to think, not just to follow the rules. Class was started with all students being asked to investigate the connection, and every child, regardless of their ability level, participated in an initial discussion, which sounds a lot to me like the beginnings of a differentiated classroom. Children were then encouraged to follow their own lines of inquiry. And as she did this, she found a way of thinking that worked for her, Emma, and she was able then to extend that into other activities. For example, the professor or the teacher here talks about the handshake problem. Emma was able to solve it quickly because she saw the connection to the polygons problem. There are other ways I could phrase this problem or differentiate it. What would happen if I had started with a triangle instead of a square? I mean, what does it mean to have a diagonal in a triangle, or does it? What if I use different words? So if I use corners versus vertices and sides versus edges, would that make a difference in the way the children approach the problem? All the polygons that were shown were regular polygons with equal angular, all sides equal in measurement, and equilateral, and I do this all the time, equal angular are all angles equal in measurement, equilateral, all sides have the same length. Is that important? What would happen if I started with some irregular polygons? Good problems, as opposed to homework exercises, often generate more questions and new lines of inquiry, provide multiple inner points for the students, which offers more opportunities to differentiate. And what's really nice is I've often seen some of the students who struggle with those homework exercises come up with some really great ways of solving these types of problems. Well, one of the other conversations or problems that I really like is the border problem. Joe Bowler, who's a professor at Stanford, has worked with a number of teachers, and I will say that Jo is anti-ability grouping, in part because she grew up in the UK system where testing is a critical point, and it's very much an ability group activity that closes doors as opposed to the revolving door kind of approach that Renzulli and others have advocated, where students can move in and out of systems as they're ready. But what she does do is a very nice job of developing this program. There's a book out of Heinemann that actually has a video of this. But let's just look at the problem for a minute. If I presented you with a checkerboard and asked you to find the number of outside squares on a board, we could count them. But without counting them, is there a way that you can figure out the number of squares out there? What I would ask students to do is to think about it, and maybe not give them more than a short period of time, 30 seconds, minute or two, and then to share their strategy with a neighbor, and then gives me two things. One, I'm hoping that there's more than one strategy you come up with, and two, that there's a conversation where everybody has a chance to share their voice, as opposed to that one student or two students in the front who always want to contribute. And then after we've done that, we want to share the strategies. And the next slide is going to show you several strategies that came up from a problem-solving session that did this, in which we have 6 different ways of doing it. And now, which one's right? Because that's the first question I'm going to get from my students. Which one's the right one? And my answer is they're all right. And why do you think that's the case? So I want the kids to speak about that, to explore this, to look at different opportunities to do that. And if we were in a workshop environment, I would give you some time now to sit down and actually come up with that. But because we are pressed for time, let me go along these lines here. We have multiple strategies. They all come up with the same solutions. They all give me the right answer. So unlike that gentleman earlier that I shared who was upset because the students didn't solve it the way he was taught, I want to encourage students to find different ways to do a problem-solving solution. We could ask kids then to extend and generalize this. Pick a different 6x6 grid, 2 strategies, using different strategies to find out how many are on there. Try a bigger grid, try a smaller grid, trying a grid of undetermined size. Is there an algorithm? Can you develop a procedure or formula that will allow you to solve any problem? So if I told you had a chessboard or a grid of 1,500 by 1,500, could you quickly tell me how many are on the border? And then once they've played around with that and found a way of doing that and come up with different strategies, can you show me how they're all equivalent? And as we generalize the solution, we all come down to the same one. If we let n represent the number of squares in one row, and we substitute that number into any of the 6 strategies they come up with, they all simplify down to the same formula, the one that the students who were looking for formulas at the beginning of the problem were trying to find to begin with. The advantage here, I can generate this formula at any time that I want to by using any of these 6 strategies. I don't have to rely on my short-term or long-term memory to recall that, yes, there is a formula out there. I have the strategies to help me develop that in the future. A much more powerful way of doing it. And then we talk about the fact that we need to be able to investigate questions in different ways. Paul Lockhart, if you haven't read his book, The Mathematician's Lament, I think you would enjoy that as well. Mathematics is not so much about getting the right answer, although I want those right, precise answers. But if we can't explain our work, then we lose the beauty of mathematics. We lose that motivation out there. As I'm scanning through the chat comments here, this creative stuff, I think Gene just put up, it brings in the motivation and challenge out there. My research started with creativity and what that really meant in a mathematics kind of setting. But working with Scott Chamberlain at University of Wyoming and some others around the country, I'm more and more convinced that it's the enjoyment factor, it's the engagement factor, it's the motivational and affective components of mathematics that really bring things into it. I'd like to say that I'm probably an abstract algebra person with a little interest in matrix algebra. And so I was never really interested in geometry. I didn't see those connections until I saw an integrated class where geometry and algebra were taught side by side. And I started to see those connections. I could start to visualize what the Pythagorean theorem meant from a geometric perspective versus an algebraic perspective, and to start to see those connections between the different disciplines within mathematics was extremely powerful. I believe that was my last slide. So we have about 9 minutes left on our schedule. I was trying very hard to make sure that I covered everything that I wanted to talk about. Are there questions that I can address? I see Taylor had a comment here about would not come close to sticking with a problem like Emma's. Well, will this work in a class of very bright or determined students? And I guess let me talk a little bit about school smart versus creative students. There's a lot of students that are very focused on getting grades, good grades, and they really are those teacher pleasers. They may be very well coached. They may be very bright students. I know that I kind of ended up majoring mathematics because that's what made sense to me. My brain seemed to work that way, although I'm not so sure that there is such a thing as a mathematical brain anymore now that I've been reading about the cognitive developments of different types of studies on how the brain functions and develops over time. But I guess what I really will go back to the title of this presentation is changing the culture. Instead of bright, determined students who are so used to getting the right answers, I want to be bright, determined students or embrace that frustration of not getting the right answer the first time, of looking for ways to solve problems that are out of the box, that are a little bit like the way Dan Meyer talked about in that little video clip. Later on in that video, he throws out a typical physics problem. How fast will a container drain if water is flowing out of a valve at a certain rate? But rather than giving them data that's nice, so that it works out with a nice even problem, and maybe even a couple of examples, he just shows them a photograph, a video, basically. I think in this case it's a hose filling a container while water is draining out of it. And the numbers don't work out nice. Real-world numbers don't. They are messy. There's things to play with. There are things that you can change and vary. And I think that's why we need students to do that. A few years ago, I went to a specialized school at a university for math and science kids, and they teach a mastery kind of focus there where students are asked to embrace that. So when the test is handed back and you only have a C on it, or you've only gotten 7 of the 10 problems correct, you're not done. You've mastered 7 of the 10 objectives, but there are 3 objectives left for you to do. And so you don't move forward, you go back and work on those 3. Or you move forward, but those 3 that you haven't yet mastered follow you along. I think too often we teach the content that the standards tell us to teach. We assess how well the students learned it, say, oh, well, maybe we'll do better next time, or maybe they'll catch up, rather than going back and making sure that those foundational concepts that they need to move on are in place. So I'm not sure I've answered Taylor's question, but what I do know is that some of my best problem solvers, most teachers wouldn't have categorized as very bright or very determined students. They were the atypical ones that maybe couldn't sit still in their seats, but worked extremely well if I gave them the freedom to follow their personal learning style and come back with an answer to a problem that they came up with. My last year of teaching before I went off to grad school for the final time, I listed the objectives that we had to master, and I asked the kids, how do we want to get there? This was a group in Connecticut that was scoring extremely low on the state standardized test. And my first year of grad school, my former principal called me up and said, what did you do different last year? Because your group went from bottom quartile in the state of Connecticut to the top number. I think we're number 3 in our SES category for testing in mathematics in 8th grade. A huge leap. And I said, I let them ask the questions. And then together we found the answers. But I guided those questions to fit the objectives of the standards. Other questions I can address. Or Robin, did you catch anything that I might have missed as I was rambling on today?
Oh, no, you weren't rambling, Eric. This has been really fascinating, and I think that people are listening intently. We've had everyone stay with us throughout the entire presentation, so that's really great. I think that at the beginning, most of the attendees were, agreeing that creativity needs to be infused into math classes. And I think you've given them a lot of ideas about how to do that.
One of the things, and I know Robin mentioned the THP columns, and if you don't have a subscription or if you're not a member of NAGC, first, I think you ought to be, but if that's not something that you're considering, I have made all my columns available on my website, which is listed there. So throughout those columns over the years, I tried to throw in some resources that you might find useful. Taylor's last comment here talks about analog versus digital, and I'm assuming, if I translate that correctly, conversationally versus computationally. And I think there's a lot of value in that conversation, a lot more sometimes in the computational piece, and making sense of things. I often get wrong answers on tests that if you had just said it out loud rather than written down the numbers, you would have said, how can that possibly be? For example, on my final exam last semester, I asked how many different ways you could roll 2 dice and get a certain outcome. And there's only 2 dice, there's only 36 possible outcomes, and yet the answer was 72. And there's no sense there. There's no making sense of the answers. And it goes back to the fact that we've taught them to follow the rules and not think about what the rules really mean.
Looks like you might have one last question, Eric, about do you have any suggestions for parents to supplement at home?
I do. And my wife and I are actually raising our second crop of kids we adopted a few years ago. And all our conversations on long car trips or dinner ask kids to solve problems, but we also embrace the fact that they're not easy problems to solve. I remember when he was 3 years old, we used to do the how many legs in the barnyard question. So we have 13 legs in the barnyard, and there's some combination of chickens and cats. And of course, he comes back and says, well, it's an odd number, so how can you do that? Because animals either have 2 or 4 legs. And I said, but there's a 3-legged cat in the mix. So I purposefully created a situation that wouldn't make sense, to force them to ask those kinds of questions. There's a lot of great resources online that you can do. I like, and I'm trying to think of them from my website. I know I've listed many of those there. But I guess it's to get the kids to think beyond what's going on. Khan Academy is fun, but often it's rule-based. But if you look up Vi Hart's work, and she used to be independent, but she's now in Khan Academy, I've introduced some kids to that, and they've been lost in her work to the point of, they're disappointed that there's not more to look at. There's a nice book if you have a student who's really focused on mathematics by Ian Stewart called Letters to a Young Mathematician that talks about his development from high school to college to his PhD status as a mathematician. And I think the more you can expose them to games and to strategies and to ask them why they chose the things that they did, to get them to think about the problems that they're solving, not just looking for that answer at the end. Those are the things I think that make it. I can teach you rules all day long and make you a great calculator, but it doesn't necessarily make you a great mathematician. I think mathematics is much more about the thinking process than getting the answer. One book that I think is good for families, teachers, everybody else is Kathy Seeley's book, Faster Isn't Smarter. And there's some really interesting conversations. They're all short vignettes with some conversations. Some of those would spawn dinner conversations. Some of them would spawn conversations with classroom teachers. And I think you would enjoy that. There are several vignettes actually on the publisher's website that you can do that. Again, the textbook is Faster Isn't Smarter by Kathy Seeley, a former president of NCTM. And then our parent group here at NAGC does some really nice work on things to do that.
Great. Thank you, Eric.
Welcome.
Thank you so much. And thanks, everyone, for joining us today. You can listen to the recording immediately after the event or anytime later on. And thanks again, Eric, for sharing your expertise with us today. We so appreciate it.
Thank you.
Everyone can disconnect. Thank you.
I will hang up.
Okay.